system, but at least that okay, Nate, but you're not seeing my screen. I am sharing now the screen. You should see just my Skype window. If I now put this presentation, okay, and you see the screen. Okay, so what I said, you know, the next lectures NTNU has recommended. No, I'm recording the video. I'm recording it with this. Is recording everything that's happening on the screen, on my screen. Okay, so I will share the video as usual after the lecture. Okay. Yeah. You know, when I'm going to use a PowerPoint for today's class. So if I'm going to need, I won't be able to see the chat, I think, when I put it on full screen. So if you need me ask any questions, I need you know, you to use the audio at least during that time. Okay. I will try to be checking constantly the chat, but you know, in case not, just scream at me through the audio. Yeah, so I hope all of you are doing well. NTNU has recommended to use, instead of Skype, to use a tool. If you go to Blackboard, they have a tool called Blackboard Collaborate Ultra that apparently you can do the same thing as Skype, but it's supposed to be better. Okay, so we can try maybe that option. I will let you know for next lecture, but essentially you have to log into Blackboard. It doesn't look very promising. It takes some time, but you have to log to Blackboard, to on the left side Blackboard Collaborate, and then I'm going to create a session, and there we can, you know, the same functionality that Skype has, that you can share the screen, you can get comments from people, also you can share the screen if you need, but that's what they have recommended, so we can test it maybe on Monday. Okay, if not, we do it through Skype, or you know, I think for now it's working quite okay. Also, for the lecture today, there is a file that is called pre-lecture on my website, on the class files with the date of today. So you get all the slides that I'm presenting today, and also you get there are some slides with free space that I'm going to do some sketches. I'm going to do some annotation. Okay. So if you want to open it and use it also to make your own annotations, that's also fine. Okay. Yeah. Another thing is that I uploaded, I think that's the final version, unless we find any more errors, but that's the final version of exercise set 1. Okay. Exercise set, there won't be 2, only 1 exercise set. And the deadline is going to be on the 12th of April. Okay, it's going to be by this Sunday, tentative. We can stretch it a bit more if you guys need more time, but I think you just have one more problem. I thought initially to give you a problem using LedaFlow, the software, but there are some uncertainties about if you're going to have access to the computer lab, if this software, we can install it on farm and you can run it remotely from your computers. So I suggest just to keep it outside, and if not, we do it in class. Okay, so if we have access to LEDA, we will do it in class. So the first part of the exercise set is just as before. I added one clarification on this discount factor, this FD. Okay, what does it mean? Using this picture. Okay. so that because it's a bit tricky, you have to find out what is that value representing, what is that factor representing, to be able to assume like a range, and then you use a uniform distribution for problem 6. Okay, but I just wanted to show you what does it represent, so you can compute it from the results. I suggest you use the results of problem 1, because there you had to use different plateau rates, and then you more or less know how it changed. You can also even change the discount rate and see how that affects the factor. Okay. And then the new problem you have is this problem 7, which is we have heard it before from these guest lectures, that we have the subsea compression station, we have the manifold, and then the production is split in 2 flow lines that they go to this Oscar B. We have had, I think, already 2 lectures on that. So your main task, and that's related to flow assurance, is to see if you're going to get hydrate formation in this pipe, and then to determine how much make you have to inject. Okay, that's the profile of the pipe versus length versus depth, and for the second part, that's the part I took away, this concern about blockage and slugging, because for that we need a transient simulator. That's not something we can do in Excel, and for that I had the intention to use LedaFlow, but let's try, if we get access through farm, or we still get allowed to go back to the campus, we do it in P2, okay, but we do it in class. So that's the main question. You have to compute pressure and temperature, then you have to see if there will be hydrate formation, and then you have to determine how much MEG you have to inject. Okay, and then you have some guidelines, some theory that tells you how are we calculating things, but essentially all of these are programmed for you in VBA. Okay, so it's only one extra problem, and the deadline is for after Easter. So I just want you guys relax. You're not stressed, and you still have enough time to deliver. Okay, the whole package will be just one exercise set, and that will be worth 40 points. Okay, yeah. So now going back to our topic for today. Let's see what we have done the last lecture. Okay, last lecture we were looking into solving the same reserve estimation problem. Okay, that we have this simple equation multiplying all of these factors that are uncertain, are uniformly distributed. The recovery factor is triangularly distributed, and how to solve it using a decision tree. Okay, a probability tree. So I told you the compact notation is something like this. Okay, you have the different layers, you decide how many branches you want to use for each layer, for each variable, and then you simply have to make the element-wise combination of all of them. You can do it in Excel. I told you we can do it in Python, and that's how I have solved it for you in class. The main important thing here is you have to see how do you discretize a continuous distribution, how do you make it into a discrete distribution, okay? Because usually we have continuous distribution, like we have been working with uniform, triangular, we can use normal, but when you are using decision trees, you have to discretize it. So there are different ways to discretize it, and I gave you all of these methods, but actually in this course we're going to use just 2. One, which is the one that you're going to do in the exercise set. I think it was here someplace. No, it's in the exercise set. Okay, one that was given at the end is this one. Okay, where you sample on the PDF, you read the value, and then you simply normalize. Okay, and you can make any samples as you want. The advantage of this method is that, for example, if you're going to capture the tail of the distribution, okay, like in this case, you have some areas that have very low probability. Okay, if you use only 3, for example, you are going to capture probably the central area, okay, the P10, P50, P90, but you're not going to capture these variations. So you're going to be missing some cases. So that's why this approach is like a bit desirable to capture. If you can put a point here, for example, has very low probability, but still the point is there. Okay. Um, what else? Also, we discussed another method that has been given in the exam in the past. That you, in the other method, you were defining the values, okay, that you wanted. In this case, you define the probabilities. Okay, and then you find the values such that the two areas to the left and to the right, they are the same. And we mentioned we do that by either I, or you can do some integration, and then it becomes a bit tricky to make the two areas the same. Okay, but essentially it's a different preference. The user here wants to get a particular probability. Okay, they don't want to risk it that when they sample on this one, they, for example, sample and they get one that has very low probability, and here they have one that has very high, for example. Okay. Yeah. And then we defined on the last lecture we had, we defined like a tentative schedule that probably we're going to have to do through remotely. Okay, so we are working on, I still had a shower and I still, change in new clothes, but I guess some of you are in your pajamas or, okay. But probably you're going to do it in the same way remotely. I hope it works fine. So we have offshore structures at least for the next two, this lecture and next one, and maybe some final remarks. We will do an exercise in Python. Hopefully, we usually do it in Excel, but let's try this year to do it in Python. And then we start with flow assurance. And this part on LedaFlow will depend if we can get it installed on farm, okay? Such that each one of you can run it on your computer, but on the server, like pulling up the server, like you see, just visualize the user interface on your computer, but it's actually not running on your computer, it's running on farm, okay? But let's see, let's keep that. If not, we are going to substitute that part by ESP, okay? Okay, so let's go for any questions before we go to topic today. No. Okay, so I have prepared, I'm going to teach it with the topic for today with PowerPoint presentation, and I'm going to make some annotations. That's why you have some blank slides that they are, saved for that. So the topic is just something happened. I'm not sure why it doesn't go full screen, but yeah, I guess this strip doesn't matter. Okay, so as I told you, most offshore fields, they have an offshore structure. That's where you have the manpower, that's where you have the people, personnel, that's where you have the processing facilities, that's where you have the export facilities. You have many things inside this offshore structure. There are some cases when you're close to shore, or some extreme cases where you send like a flow line, a pipeline to shore, that you don't have this offshore structure, okay? Or you have some trends now, people are trying more and more to get rid of the offshore structure altogether, and to have like everything subsea. Okay, they call it the subsea factory, and it's like a wish that the industry has, a goal, and probably we will see more of that in the future. But for now, what is most common, most traditional, what has been working very well is to use offshore structure. Okay, and offshore structure, it's also one of the main parts of CapEx, and it's also one of the very important part of the field. Okay, so we should at least see is dedicate some time, because it's very expensive, it's affecting cost very much, it's affecting the value, the revenue, net present value of the project, the economic performance, and also can affect very much our operation. Okay, so I think it's good, you won't become an expert from these lectures, okay, and I hope you don't fall asleep, okay, but simply just to get a taste of what the offshore structure looks like, what things do we have to take into account when deciding upon an offshore structure, and what are the different options we have, okay. There are more advanced courses if you go to probably the marine department, where they teach you more in depth about these structures. But I just want to give you a taste, because I think if you want to know about field development, if you want to be working on field development, or even in offshore field, you have to get a bit acquainted how it looks like. Okay. So some components you have in offshore structures are, so you can have, I'm going to say here, you can have or you cannot have. Okay. You can have facilities for drilling and full intervention. Okay, you see here the drilling tower, BOP drilling floor, mud package, the mud that you use to control, to be able to lift the cuttings, to cool the bit, to be able to control the pressure, that you don't have any kick of fluids, reservoir fluids to the bore. Cementing pumps, storage decks for drill pipes and tubulars. You see them on the right. You see the pipes are stacked. You have the drill pipe, and you have the tubing, casing pipe, drilling risers. So if your offshore structure has these facilities, that's a big thing. Okay? It requires significant amount of space, it's expensive, and we will see now it also depends on the capacity of that drilling rig. Okay, if you want it to drill deviated wells that are extended reach, very far away, then you're going to need quite a robust and big offshore drilling package, which is going to make the structure also heavy. Okay, also heavy and more expensive. So the next thing we have also is facilities for light well intervention. That's something almost all offshore structure have. Okay, some sort of light well intervention. And here we're talking about coil tubing and wireline. We don't have to put a BOP on the well, but we can actually enter through the swap valve. Okay. And these are for light intervention if you want to make logging, if you want to make some sort of light operation on the well, you can do it with these two. Okay, use usually coil tubing, wireline. You can use tractor. And we are going to see now that's only for offshore structures that have dry Christmas trees. Okay? We're going to see now a difference between dry and wet. There is a very important difference. Something that almost all offshore structures have in common is processing facilities. Okay? Where we have, if you remember your processing course, we have oil, water, gas and water separation, physical separation of phases, and stabilization. You want to bring part of the components, most of them to the liquid, because that's what pays more. You want to bring from all the molecules, you have hydrocarbon molecules coming out of the reservoir. You want to send most of it to the liquid, okay, because you can sell that at a higher price. And also to separate physically these three phases. You have water, oil and gas, and maybe we should mention here also solids if you have any. Then you go to produce water treatment, where you have, after that you have either disposal or reinjection of water. Okay, disposal to sea or disposal to another formation that is not in use but simply will be for disposal of water, or reinjection, which usually is for some sort of pressure maintenance or EOR. Okay. Then on the oil you have dehydration, does not done that much in Norway. You have desalting, the oil also is not that high content in salt, and stabilizing further, and then you send it either to a tanker or with pipeline, at least offshore, that's the way it is. And then you have dehydration, which is typically made by the TEC, triethylene glycol contactor, which is a big equipment, a tower, where you take out part of the liquid from the gas, part of the water from the gas. And then after that you have this guy, gas compression, which is one of the guys that are the most energy eating parts of the field. Okay, where you big compressors where you have to compress this gas and either send it to export on what is called a rich gas pipeline, or then you can re-inject it to maintain pressure. Okay, so that part is like the core and one thing that is almost always present in an offshore, in the main offshore structure for oil and gas production. Okay, then you have gas injection system, gas compression units for pipeline transport, water injection systems, and they eat a lot of power, and they also eat a lot of space. They are heavy components, machinery. Yeah, that's like, I guess all of you have seen a separator, how it looks like, the internals. Then we have other things which are living quarters for people. We don't have that many unmanned facilities in the world offshore, but we have a few. But they are, like we will see now, they are just one offshore structure. But it's one of the offshore structures can be unmanned, but all the rest maybe are manned. Okay. Helideck, you see it here on the figure. Power generation, we have usually is done through a gas turbine that is run on the same gas that you're producing. The flare system, you see the flare here to the right sticking out. So that means you have here someplace the process, okay, the whole process that I described. And then you have the flare for emergency situations or for maintenance, or for that you have to burn some hydrocarbons just to make it safe, that you don't have a release of hydrocarbons in your process, okay, your platform. Some utilities, hydraulic power fluid, that is to remember to operate most of the valves. They are operated remotely through a hydraulic system. Every valve, you have chokes, you have the master valve, you have the process valves. All of them are operated using hydraulic fluid, compressed air. You have drinking water, air condition, ventilation, heating system. Okay. One thing that is also, I would say, optional, or that you might find or not find, is you have a bay, what is called a well bay, for wellheads and Christmas trees. Again, it looks a bit like that, but essentially when all the wells, and we are going to discuss that more in detail later, but when all the wells reach or are drilled from the platform, then that's what you call a dry Christmas tree. Okay, when you have access, you can have actually a person come and stand here next to the Christmas tree. Okay, and that's the bay, that is the housing or the area where you have all the Christmas trees of all the wells. Okay, and on top of that, usually you have another floor where you have the intervention, light intervention. Either you have the drilling package, the drilling tower, or you have the light intervention facilities, okay, on top of this. And that drilling tower usually has a way that it can move from to be exactly on top of the well. Okay, it has some skids that it can slide and can, just be placed just on top of each well. That also has a problem that if you are doing intervention or you're doing something in a well, you cannot be, all the other wells have to be usually shut in. Okay, they have to be closed. Because you see the space is quite tight, and if you're doing any operation on one of these wells, then you risk it. There is a high risk that you're going to, with the drilling string or with the BOP, you're going to knock down some of the others. Okay, so that's why you have to shut down production. Other thing we are going to discuss also today, or maybe on Monday, will be production manifolds. That you take you commingle the production of all of these wells, and then you send it to the separator. And usually on the platform we have not just one train, but we have two, usually, trains. So you can decide to produce to one train or the other. Facilities for oil offloading. We will see a bit now how that looks like. Control system, monitoring system, and also system which is very important for storage, injection, and recovery of production chemicals. Okay, that we need. That's the flow assurance part we will see later, but we need wax inhibitor, scale inhibitor, hydrate inhibitor, corrosion inhibitor. We have all kind of chemicals we mix with the hydrocarbon fluids to avoid problems. Okay, to avoid these flow assurance problems. And we might have also a repair workshop. Here is what I mentioned, this offloading facility, that you have the main platform, a jacket, that's called a jacket, and then you have the export pipeline, and you have a buoy where the tanker is connected, and they can go and load just load off the oil. Okay, let's see why. Can I get rid of? Okay, like on a jacket, you see here some parts. You see the flare, okay, production module. They are usually divided now. They are making in a modular way. So you can have one company delivering all of these modules, or you can have one delivering all of them. But it's usually made in a way that is modular, such that to mount them is slightly easier. Okay. So you have the wellhead or the well bay module. You have the production, which is the facility, the processing facilities. Then you have also another production module here, water injection, drilling. You might have, the mud package, the cementing pumps, and then you have here more closer to the living quarters. You have the heli deck, and you have power generation, and you have also the utility module. One thing which is critical is that usually you want to put the processing facilities where you have live or you have processes that are working with oil and gas as far away from the living quarters. Okay, and also you have to be very careful, depending on the direction of wind, that when you have the flare, that the smoke doesn't go doesn't flow against the platform. Okay, that's a kind of an old platform in the Norwegian continental shelf called Valhall, and you see that in this case they are spread. It's a whole field, but it has several offshore structures. Okay, of course, depending on the size, you can afford to have several structures. If not, you try to compress everything into one because it's cheaper. But if you can compress it, you see here you have one module where you have the drilling towers. So probably here you see all these pipes coming down. These are all the wells that are just drilled from here. Then on this part you see the flare, and you see also the flare here. So you suspect, I have to admit I have been in this platform before, but I don't remember. I think here you have processing, and here you have some processing, but you also have the living quarters. They are here, and the operation center, I think it's also here. Okay, and then you have, I don't know if here, maybe I think you have some wells here, but you don't have the drilling package. Okay, so we're going to see that case later. And here you have another living quarters and heli deck. Okay, so it doesn't have to be in one place, but can be spread. Yeah, I hope no questions so far. Okay, I hope you're not falling asleep. Okay, different types of offshore structure we have, and first we have two categories, which are if it's bottom supported, okay, that the weight of the structure is laying on the ground, okay, on the soil. And there we have two further categories. One of them is fixed, that it's do you have the common jacket, okay, and the jacket you have the piles. You have some piles that are hammered into the ground, into the soil, to fix it to the soil. Okay, and they are made with this structure, which is a jacket. It can be often is a steel jacket, and you have the facilities on top of that jacket. Okay, very much used. We are going to see in some moments when do we use it. Then you have another type, which is GBS, or gravity-based structure. They are typically concrete structures, and they are made such that their own weight, they don't need to be, usually they might have some skirts, okay, some steel skirts that they bite into the formation, bite into the soil, and then that helps to keep them more stable, okay. But usually they are simply withstanding there by their own weight. And this was the concept used for many years in the North Sea. Norway had a strong concrete industry, and they were manufacturing these structures for the oil and gas industry. Okay. Then you have a jackup. The jackups are not that commonly used for oil and gas production. Okay, they're mainly here we're discussing only for oil and gas production, not for drilling. Okay, drilling is a different story. Jackup are mostly used for drilling, but sometimes they are used for production, but not very often. Okay. The main thing here is that they have some legs that they are also made in some sort of a jacket structure, but they have some motors and some gear system that they can pull them up, and then it can be simply floating, and then when it reaches the location, then the legs are deployed down. Okay, they are simply lowered down with this system mechanism of motors and gears. Okay. Compliant tower is similar to jacket, but actually for very big water depth, then if you want to make a jacket, then the base will be very thick. Okay, simply will be very very spread, so they will be very costly. So for big water depth, they use this concept, which is they keep more or less the same section, and that of course causes some issues, some movement on this compliant tower, especially at the top, to the right and to the left. But still, the movement is quite limited, or is quite moderate compared to the floating structure. Okay, and that is, I think there are some examples, mostly in the Gulf of Mexico, where this is used, and it's simply a way to expand the reach or the depth on which a jacket can go. Okay, but they have some movement. Most of them, they have no movement at all. At the top side, they have some movement, but it's really very, very, very limited. Then we have the floating structures, in which, I don't know if I put here, yeah, in which they do have significant movement usually. And a floating structure can have movement in different directions, can have up and down, front and back, can have right and left, and can also have all the associated rotations. Okay, can have what they call roll, pitch, and yaw. Okay, we're going to see that because the way these structures move, depending on the sea conditions, there are also it's also another thing we have to take into account when selecting structures. Okay, but we're going to see that at a later stage. So we have FPSO, which FPSO stands for floating, production, storage, and offloading. Okay, and it's called has a ship shape. It has basically has a ship. The structures are usually moored. Okay, they have some kind of mooring, either by chains. They have also some ropes. Okay, tethers. They have also some composite materials made out of mix of plastic and steel. And they control the ballast. Okay, that's something very important you have to keep in mind. They move considerably. They are moored, and they also have to control the ballast. Okay, because that gives them the flotation or how far away the top side or the deck, okay, is from the mean sea level. Okay, so if, for example, you're loading too much, in this case, the FPSO loads most of the production, oil production, is on the ship. Okay, if it starts loading too much production, that's going to affect the ballast, the floatability of the vessel. So you have always to be controlling the ballast. Okay, then you have a semi-sub, which are typically used for drilling, but there are some production structures, but for drilling they are very commonly used. Sevan FPSO, that is like this ship FPSO, but it's like a circular shape, and we're going to see now where the idea came from. Spar, which is like a big cylinder, which goes very much deep, and the intention is that on the spar you have most of the body is underwater. Okay, or the biggest part of the body of the spar is underwater, so that actually helps it to be stable. Okay, to reduce the movement in the spar. And then you have this tension leg platform, which is the only one. All of them are floating by itself freely. Okay, but this one is, you attach some tendons, you attach some tethers to the seabed. Okay, and then these tethers are actually in tension, so that they are pulling the structure down. They are pulling this TLP down. Okay, if they were not in place, the simply will float up and will be flowing much higher. It will be unstable. So these tethers, they are in continuous tension, pulling it, bringing it down. Okay, and that's why they call it is positively buoyant. Okay, I think we can just take these two and then we take a break. We also need a break even if we are taking things online, right? I don't hear anyone snoring, so that's a good sign. But all of you are muted, so that's probably the reason. Yeah, so that's the jacket. You see the cross section is increasing with depth. Okay, and then you have the piles, okay, that are simply hammered, usually by hydraulic hammer, or they have some other way to hammer them into the soil, just to make it by itself, by its own weight, is not going to stand in place. Okay, if a wave, a current comes, it's going to probably move it and shift it, and will be a big catastrophe. So in this case, they're using these piles simply to keep it in place. Okay, depending on the soil, the type of soil, you might have to go deeper, might to use bigger piles, or you may have to use some other methods to stabilize. Okay. Something is, if usually jackets are used for low water depth and for dry Christmas trees. So the wells are drilled just like onshore, but simply they have to go through this water layer and then reach the formation. But everything, conductor, you have all the surface, intermediate casing, production casing, they all go all the way to the deck. Okay, so it's just like an offshore well, but simply drilled from a platform, from a steel platform. But you see, you identify very quickly because you see all the legs and you see some big concentration of pipes, and you see, well, that's where the wells are coming up. Okay, you have this system, which is some sort of a diagonal bracing that is supposed to give you more structure, more rigid, to make the structure more rigid, and also to make it more, to have a higher resistance. Gravity-based structure, concrete, what I mentioned before, is standing by its own weight, so it's a very heavy structure. It might have some mechanism to fix it to the ground, like it has some skirts that they bite, or some skirts, steel skirts that they bite into the soil. Might have some suction anchor mechanism. But the main thing so you see some of these structures like Gulfax, Troll, they are having this shape. And one of the main advantages is you have storage place in these tanks. Okay, so you can store, in the jacket you cannot store anything. You need to have a tanker nearby, or you need to be able to store that fluid, those fluids. You don't have storage any place. But in this gravity-based structure, you usually use the legs to store fluid. Okay. Actually, I'm not sure if you heard, but there was quite a long time ago in Norway was one of these structures that was being transported outside from the fjord to the sea, to shore, and then it fell, and then it was an issue, it fell, and then actually it hit the seabed, okay, and it caused like a mini earthquake in the region. Okay, I think we take a break, okay, if nobody wants to ask any question, and we come back. Let's say, do we take a kind of a regular break, 15 minutes, to stretch the legs and drink some water, and then we come back with the rest of the lecture. Okay, I'm going to leave this open, so I'm just going to mute my microphone and just stop the recording. Okay, let's see that gets the audio. Yes. Okay. I just want to let you know that normally in previous years I have taught this part of the course using a journal, but I think sometimes you might get a bit frustrated if because I need to use a lot of figures. Okay, I could make, but it will take a significant amount of time to make these sketches myself. So the way I do it, I copy and paste to journal, but then I think some of you might get frustrated because your notes get all spoiled because you cannot copy and paste, you don't have the images, and then all your notes have empty spaces. Okay, so that's why I have made this here to do it through PowerPoint, which I don't really like too much, but then you can have this beforehand, and then you can make your annotations on the slides. Okay, just I hope maybe that's better, but yeah, any feedback is appreciated, and you know, I try everything's new things every year, so it's just a matter of trial and error to see which one works best. Yeah, so going back to our yeah, presentation. So we have a gravity-based structure. Sometimes also you will see some of these structures in offshore Canada. Actually, there was a field recently developed using this concept. So it's not something that nobody is using. It's only a few people use. You need to have concrete industry, and you need to have special knowledge to, you have to deal with leakages, stability of concrete, lifetime of concrete, but is also done. Okay. Jacob, what I mentioned before, that's from Volve. I'm not sure if you're aware, but Equinor, they released data from this field called Volve, a small field that produced, I think, for 10 years, and then they was decommissioned, and they released everything. So they have production data, drilling data, they have reservoir data, everything. And you can get, if you just sign up, you can get access to all of this data. So this image is taken from the PDO, and it's actually saying that instead of using, because they knew they were going to use like a relatively short time it's going to produce, so they, instead of using a jacket, they decided to use this jack-up. Okay, a jack-up, actually what I told you, these legs, they come out down, it's initially floating, they come down, they sink on the ground, and then it simply this one starts going up, okay, and separates from the sea level. FPSO, which is something very popular, you see it many fields, especially for subsea fields. In this, you see jacket, I can still get jack-up, GBS, I still can get wells like they were onshore. Okay, they are drilled through the legs. So when you see the process diagram of these fields, I think I have one, but probably have it on paper. I usually bring it to class so you can see. But the wells are arranged in these circular legs, okay, because wells are usually drilled, in this case probably they're drilled through here, okay, or also here. So they are arranged in this, the well bay is essentially one of these legs. They go through these legs, okay. The jacket also the same. FPSO doesn't allow that thing. Okay, FPSO simply doesn't have any drilling facilities, simply is processing, okay, and people. You see the heli deck. Something very important about FPSO, and here we have our first sketch, just to say we are doing some engineering, right? Is that the FPSO, let me change the color. The FPSO is essentially a ship. Okay. So it has significant movement in this direction, okay, in this direction, and also has significant rotation. What I told you, it might have rotation in this direction, has rotation in this direction, okay. And what else are we missing? Rotation here, and also rotation in this axis. Okay. But we connect, so typically what we have is like we have subsea. Okay, let's put the seabed here. I hope you are seeing the drawing. If not, just remember to scream. Okay, we collect all of this production, and then comes with a structure that is called a riser. Okay, it's collected for different whales, or it might be each whale has its own riser. We are going to see later that can also happen. You might think why, okay, but that can also happen. And you have, make it a bit nicer. Not sure how you can erase here, but okay. Let me see. Okay, so a bit of a disadvantage to use PowerPoint to make sketches. So you have usually riser might be directly, it goes a bit like that, and then you have the vessel, okay, the FPSO. Okay, but due to the fact that the vessel is moving, okay, continuously up and down and in all of these directions, so this pipe has to be in a fixed location. Otherwise, it's going to get all bended and it's going to get all damaged and it's going to get all deformed. Okay, so this pipe has to be fixed. Okay, while the FPSO has to have the chance to move, to be able to move. Okay, or we don't say fixed, but more or less plus or minus fixed. Okay. It won't be fixed completely. That's why you have this strange shape that is like going up and down, and you have all kind of designs simply that are trying to absorb the movement. Okay, some sort of movement, but they cannot. Also, one thing with the FPSO is that the movement depends also on the direction of the flow. Okay, of for example, the waves. Okay, you always have in a ship, you always have to align with the direction of the waves. Okay, if for example now the waves come on a different direction, okay, then you have to reorient the ship. Okay. Or if we'll do one more so it looks nice. Okay. But you cannot do that with the pipe, so you have to rotate the ship to take into account the changes, for example, in wind and the change in wave, okay, and also the change in sometimes of current. Okay, but if you do that, then you will be twisting the pipe, okay, which is not the intention. So what is done, you create a structure in the center that is not supposed to move, that is called a swivel. Okay. And that structure is actually going to be fixed in place. It's going to be, that's the structure that is going to be moored. Let's try to change color here. Okay, so that's the part, this swivel that we have here, and we are going to see now very quickly how it looks like, is what is going to be more to the seabed, and that is going to have less movement. At least it's going to have maybe movement up and down. Okay, it's going to have some lateral movement, but it's not going to have to rotate. Okay, which that's something we have to make continuously to take into account weather changes in an FPSO. Okay, so that allows actually to make that accommodation. The FPSO is constantly, of course, it depends on the conditions. Okay, if I have, let's put here the comment, if wave conditions vary significantly, at least it looks like I have better handwriting in PowerPoint, right? Yeah, then it has to be adjusted. If not, simply what you will see, and you will see a figure. Let's make it with another color. Okay, you might see simply that the FPSO has the riser simply coming to the side. Okay, or different risers coming to the side of the FPSO. And in that case, you don't have a swivel, but then in that case, really you have to make sure that you won't have any change. So you have to be sure that you don't have any change in direction of the waves. Okay, of course, if you see here, if I don't change the direction and then I start to get significant waves on this side, you might get a problem that is going to tilt, you're going to have a catastrophe. Okay, so if not, if let's say if still, let's call it still or quiet weather conditions, here. And here I'm going to show you, I'm not sure what, yeah, so here is the swivel. Okay, so you see the swivel can be located, you have here the mooring lines are, I'm not sure if you can see very well, but you have the mooring lines are these white things that are holding the swivel into place. And then you have all the risers coming up on the swivel. And in this case, the swivel is actually located at the edge of the vessel, okay, just in the point. And that is the swivel. And the boat can rotate to the right or to the left, okay? Okay, and I think here there is some animation showing that the fluid goes inside, and it's a bit special because you know one part is rotating and the other part has to be relatively fixed. Okay, so we are going to see now how it looks like. Okay, courtesy of YouTube. Okay, you have the links of each one of these videos there, but you see how the swivel here looks like. You have the part which is fixed, and then you have the other part which is rotating, and you have different things because you might have for each well they need to be you cannot commingle, but they have to be, you know exactly where it's coming from. You might have from different fields operated from different reservoirs operated by different companies. You might have also not only that you're producing from all of them, but you're also injecting. Okay, you're also injecting gas and water. You have also the power lines. You don't have only fluids, but you also have other things. Okay, and here is what I told you. If you don't need a swivel, if the sea conditions don't change that much, if there are relatively still and calm seas, then you use this. Simply you bring the risers on the side and you don't need a swivel. Okay, that's another more details on the swivel, how it looks like. It's a high pressure swivel, and they show you like all the different connections they have, but let's focus now just on one. Okay, goes in the center, the fluid, then goes outside through this hole. Okay. Okay, and the swivel can be, okay, how the real thing looks like, and the swivel can be actually a problem if you design poorly. Okay, for example, if you were expecting some rate of water, okay, or you expected some rate of sand, and then you are getting more sand than what you are supposed to get, then you're going to get erosion because all of the swivel is tightly dimensioned for the rates that you have, for the capacities that you have. So for some reason, if you start getting, for example, too much water from the production fluid, then you have too much liquid to flow through the swivel. Okay, that can lead to erosion, can lead to all kind of problems, to leakage. So they have to restrict the flow rate through the swivel. Also, if you get sand or if you have to inject, for example, too much water, it might be that you have enough capacity just to inject that water. In the reservoir, you have enough injectors, but the swivel might be a bottleneck. Okay, so let's maybe make that comment here. Okay, when we have about the term bottleneck, that the swivel can be a reason why things can be bottleneck. Okay, because they are designed for some flow rates, and if you want to change it, it's not so easy. Yeah, the spar is also another interesting concept that I told you. So most of the idea of the spar is simply to try to limit the movement. Okay, let's see how people are doing here. Nobody's snoring, so yeah. So the main intention was to have a big draft. Okay, that means that it has a big part of the structure is simply submerged. Okay, that means that it's making it less sensitive to waves that impact or to wind. It is sensitive to currents, but it's less sensitive to waves and to wind. Okay, so that makes it more stable. That makes it that actually in a spar I can have whales that have dry Christmas trees. I can have whales that got all the way here. They are constructed in a slightly different way, and we are going to talk about it a bit later. But you can have actually dry Christmas trees here on the spar because the movement is significantly reduced because of this long draft. Okay, here you have the pride of Norway recently, which is the Osta Hansten spar, which is the biggest in the world and even has condensate storage for liquid, not spars that typically have storage. And it's actually offshore Trondheim. And it's quite deep. I think it's 1,500 meters deep. Okay, it's a gas condensate field. One thing with spar that you have to, and also with many circular shape, you see that this is a circular base. Okay, one thing that you have to be that maybe you're aware of is vortex-induced vibration. So I think this video is also from YouTube. You have the link here, but he's making some experiments to show this vibration. Okay, so let's speed up a bit. Okay, so he's flowing liquid from this direction to this direction. Okay, he's relatively shallow. Okay, he's using a bowl just to show you that he's flowing from right to left. Okay, and then he has these hangers, okay, that he's using to hang the cylinder. Okay, just to hang it and let it freely. It cannot move up and down, but it can move left to right. Okay, so you see that you get some, and we are going to see it later with simulation. You get some. The fluid cannot go all the way from here to here. Okay, it cannot. When the fluid impacts the cylinder on this side, it won't create any problem if it could go all the way here and then it continues on the flow. Okay, for example, the streamline will be knocking the right side, then following the contour and then leaving on this side. Okay, but it decouples or it detaches early. Okay, so maybe we should make a small sketch. Okay, so the fluid is coming on this direction and it actually cannot follow exactly the contour and it's going to get detached here. And this detachment causes these vortices and it causes this turbulence. Okay, and one interesting thing is that with time, that's what you have this vortex shedding or von Karman vortices, is that this detachment point, it can change. For example, it can be here, up here, it can be down here, and it becomes a cyclic oscillatory problem. So for example, when this one detaches here, that one is detaching up here, but then when this one is detaching up here, this one is detaching here. Okay? And because of that, the pressure, if you plot the pressure, okay, you have here some pressure, but when it detaches, okay, this pressure becomes negative. Okay, or becomes a low pressure. Okay, and this pressure also. So you see that the pressure, if you calculate the distribution of force on the cylinder, okay, you have some force which is applying here due to pressure, but you have also some force that is acting here on this area. Okay, and you have one resulting force that, for example, is on this direction. Let me just put the color here. Okay, so that force, if this area is changing now, for example, becomes up here, okay, this force is going to change and it's going to cause be fluctuating up and down, okay, and it's going to cause the cylinder to move up and down. Okay, that's not really. I think it's better just if you see it. Okay. Okay, so you see actually that is moving because of that. That is changing the location of where is detaching, okay, on each side. Then it's moving, is causing a force, an unbalance of force or a variable force on the surface of the cylinder, and then that's causing the cylinder to move right to left, okay, or in this case, okay. By the way, you have the links of each video at the bottom, so you can just on your free time, or if you want, you can just watch them more in detail. Okay, that's a simulation, but here you can see if you're at low speeds, then simply it splits. You see the detachment point here and the detachment point here, but when you start increasing the speed, you see this phenomena that the detaching point is moving slightly up and down. Okay, and then you have the creation of those vortices. Now what they have done is that before they were keeping the cylinder fixed, and now what they have done is they move the cylinder due to this force acting. Okay, and in this case, of course, it depends on the mass of the cylinder, but you see the movement is quite violent. I think they have one more simulation here where the cylinder has less mass. Okay, so this could be a big problem in spars, and that's why, and also chimneys, you see in other structures that have these cylinders, they can become a problem, and then they make these helical strakes. Okay, which you see the effect it has is breaks a bit these von Karman vortices. You see here is plotting for both, okay, two configurations subjected to the same flow, and it's not that the flow is varying here, the flow that is impacting, simply the flow is constant, okay, the flow that is impacting here is constant, but you are getting this simply by the detachment, okay, the detachment point is changing. So it's plotting here to the right is the force acting, total force magnitude, I think is force in X and Y acting on the cylinder, so in this direction and in this direction. And you see the scales, they are only by putting the helical strakes, you are going by a decrease in an order of magnitude on the force, okay, from 300 to 30 and from 60 to 8. Okay, so let's see how it looks like. Here you see the detachment, okay, and the forces that is causing, and you see the oscillation in the force due to is releasing up here, down here, while here you have a more chaotic. Okay, it's not cyclic. Remember, excitation, when you talk about vibration, you talk about mechanical components. Every time you have an oscillation, you have a problem with resonance, right? Because here you have a very uniform excitation. We have with a very uniform period. And if by some reason you are equal to the natural period of the structure, okay, of the spring, you're going to get big oscillations, big amplitude. That means big stress on the structure. Okay. Here you don't have periodic, you have more of a chaotic movement, but the most important thing is that the forces are much less. Okay. So I put the video here. I didn't put the name of the author or anything, but I think these are beautiful animations. Okay. Swivels and FPSO, a new concept of floating production system. Sometimes they remove the O, okay, they call it simply FPS. And simply you see here is the swivel. What you make is you don't need the rest of the vessel. You say, well, if I'm rotating the vessel around it all the time, that's causing a loss of energy, especially in an area where I have to be changing constantly. I have to be adapting constantly. You also need to have a captain. It becomes a ship. Okay, so you need to have a captain that is always constantly taking decisions of how to change the orientation of the ship. Okay, while in this case you simply say, well, why don't I take that complexity out and I simply just put the swivel, okay, and I make it simply bigger such that it can fit more things. So that was the greatness or the smartness of the Swivels FPSO concept. And there are a few, I think only two in the world, maybe one, Goliath, but they are planning to, I think, build more. Tension leg platform, also another concept. It looks like a semi-sub, okay, a bit, but the thing is that, as I told you, it has these tethers that are holding it down. So if I remove these cables, if I remove these tendons, the structure will simply float up. Okay. Looks a bit like that. Tether. This also has enough low movement, okay, because it's anchored such that it doesn't have too much heave, which is movement up and down, but it has some vertical movement, some horizontal movement, sorry. Okay. Here, it's time to make a small sketch. Okay. And the whole idea of, if we make it like a square and we put the cable connected to the seabed, okay, the idea is that these cables, they are in tension, okay, they are pulling the structure down. Okay, so if you have the seas moving, it won't have limited movement up and down. Okay, that's why you can, for example, have whales that simply can go all the way here and can still resist, can still be, don't be damaged. The more important thing is that you don't want any damage occurring on the pipe, okay, on the whale riser. But it can have movement actually on horizontally, okay, to the right. If, for example, you have waves impacting on this side, it can move to the right. The thing is that it has the TLP has a self-balancing mechanism. When that happens, okay, when you have pushed it slightly off its equilibrium area, okay, for example, let's say you push it to that side, well, you see what happens with the tendon. Okay, now the force is always going to be aligned on the tendon. Okay, but now you have two components. You have the same vertical component you had before, but now you have one horizontal component that is trying to bring it. If I have the wave pushing it on that side, this one is actually trying to bring the structure back into place, back into a location. So it's like a self-balancing structure. When it's put out of its equilibrium location, it will tend to go back simply by the strength or the pull that these tendons have. Okay, that clear? Okay, compliant tower, as I showed you before, a relatively big water depth. It's not a jacket, but it has the same principle, but it doesn't become wide at the base, but simply I try to keep the same cross section. Otherwise it will be too large, okay, to keep stable. And it has, because of that, it might have some movement on this direction. Okay, it has to be also moored and anchored. Usually has some mooring on this side, just to be able to keep it, to restrict the horizontal movement. Okay, semi-subs are also used. You probably have seen this shape many times, but they are mostly used for drilling ships, drilling vessels. And this actually is not a production structure, but it's a drilling vessel. But you see the legs, they have different locations, configurations, number of legs. They are sometimes in this shape, which is like like a catamaran, but this one has more like an octo base shape, so you can have all kind of variations. And the difference is with the TLP, these are not anchored with tendons and tethers that are pulling it down. This is simply floating by itself, and you have to control ballast to find the position. Okay, finally, we got an overview before of what kind of offshore structures we might have, which ones are the most common, the ones that you encounter, and I gave some I hope fun facts about the structure. But now we see, how do we select the offshore structure? Okay, what parameters enter into play? So first is the water depth. Like you start to think, well, jackets and gravity-based platforms, they are not suitable for very big water depth. Compliant tower, maybe not also. Also, this TLP, they have a limit how long these tethers can be and how long can they work. Okay, otherwise you have significant if, like on this case, if this distance, right, from the seabed to the TLP becomes big, you are still going to get significant deformation to the side, and then your well riser is going to be significantly deformed. Okay. So water depth is one main criteria. The type of Christmas tree, that's something that we're going to talk more in detail. You have two types, dry and wet. Okay, wet basically means subsea wells, and dry means platform wells. Okay, and that depends on a few things, but the main thing is the reservoir spread and structure. It depends on what are your well intervention needs, what kind of equipment you have inside the well, completion you have in the well, and if you need to do frequent intervention. If you only need to do, typically for subsea wells is maybe 10 years, 15 years, then it's okay to do it with that frequency. But if you have to do every year or every 2 years for some reason, okay, then it's good that you have a way to make cheap intervention. Okay, for example, with a drilling package and you have the Christmas tree on the platform. Also, if you need to infill drilling, you have a lot of uncertainty, and how many wells you have, it will depend on that uncertainty. Remember, for a dry system, you need to have this well bay. That is the system that is housing all of these wells. So if you need to make it bigger, let's say you're not sure, but you need 40 or 20 wells, then you need to have a lot of spare space. And this spare space is costing a lot of money. Okay, not only because it makes the structure bigger, bulkier, but also you'll see for some structures, it's actually, they support the weight of part of the well. Okay, so if you need to make it for more wells, for example 40, it's going to increase significantly the cost. Okay, need for storage, for example, in the case of Ostahansten, it's a remote area. You might have some weather issues, you might be isolated from the market for a few days, so you need to have some condensate. Otherwise, if the tanker cannot reach to your location, then you have to halt production altogether, okay, because you cannot get rid of the condensate. And also the last thing that we probably are going to discuss, we have a comment? No? Somebody left? Yeah, also the one thing these are like technical constraints, okay? The other thing is the marine loads or marine environment, the oceanographic environment, that each structure has some vulnerabilities or some characteristics that make it suitable for some conditions, weather conditions. Okay. Water depth. This on the x-axis I'm showing here at the top is the water depth from 0 to 3,000 meters, and you see that jackets and gravity-based structure, they usually have made up to 413 meters. Okay, the biggest is or the deepest is Bullwinkle. So if you have water depth bigger than that, you probably cannot use jacket. Okay, for that you go and migrate to compliant tower, which can go all the way, can extend that to 610. By the way, most of the developments in Norway, they are below or around 400 meters. Okay, below 400 meters, except Ostahansten, which is 1500. Then you have semi-subs that they have been used for, because they're floating, actually they can be used for any depth, okay, but they are usually used for bigger depth, up to 2,400 meters. And they usually have subsea wells, the semi-subs, although some people are arguing that they are used, I think there are a few that are used for dry, for platform wells. Then you have the tension leg platform, which the highest water depth is 1,500 meter. And then you have spar, which is 2,383 and 600. And then you have the FPSO. This here is supposed to be FPSO, which can go to the deepest, which is, I'm not sure if maybe now there is something deeper, because I did this a few years back, but 2,900 meters. Okay, now type of Christmas tree, as I told you, one of the criteria is reservoir spread and structure. For example, if you have a big unit which is not very spread, which you know you can reach with deviated wells, and it's not extended reach drilling, but it's like deviated drilling, you can maybe use like either to drill all the wells from one location or to use a single platform and use platform wells. Okay, this means that all the wells, they have almost the same departing point, but they have different targets. Okay, that means that wells have to be long and deviated, which adds sums on the cost. Okay, but also wells are drilled from one location. I told you the tower goes in. The tower is located here. Okay, and the tower is actually able to move in some rails. Okay, it's able to move in some rails. So it's moving exactly on top of the well and is drilling the well or making intervention on the well. Okay, so you don't need to spend mobilization time. If you're drilling a lot of wells which are spread, then you have to move the drilling vessel. Okay, you have a drilling ship, for example. Okay, and if they are spread, so you have to go on top of that well, then you have to unmoor, you have to move it to the next location, which is a process that takes time. Okay. However, production startup must be delayed usually until all wells are drilled, because of this safety issue. Because they're relatively close, you're working with the BOP, you're working with drilling string, so you have a chance that you are going to knock some of the wells. So usually the startup of these fields, it looks like you don't get production, but then suddenly you get all the production. Okay. Well, if we see if they are more spread, okay, then you usually use subsea wells. Okay, which means you don't have to make them too deviated, but they can be shorter and vertical, and then simply the horizontal section, which is cheaper. But the drilling rig then has to be mobilized. Okay, has to be transported, has to be placed on top of the well, and then has to be drilled. But here, usually, because wells are, if you have already the topside in place and the pipelines in place, then you can see this production profile. Here we should put time and then Q rate. Okay, you see that you have, when wells are entering into production, you have this nice ramp up, which actually gives you oxygen. Okay, here if this time is too long, then the company is struggling because it doesn't get revenue yet, but here you start to get a stream of revenue. Okay, but also one comment is that the more spread then requires a bigger and costly drilling package. Okay, because this has to be able to reach the targets that are far away from the location, and you can if you're going to reach everything on the structure from one location. Okay, so that means if the drilling package has to be bigger, has to be extended reach, then that requires to have more weight on the structure, and then the structure has to be bigger, which is very costly. Okay. Another thing is that well weight. Okay. So typically, let's see how we can do this with not too many colors. In onshore wells, okay, you drill first the conductor, right? Or you jet first the conductor in place, then you, let's say here is the mud line, okay, or let's say simply the surface. Okay, this one, pointer. This guy we call the conductor. Then I have a surface casing. I'll just use another color. Okay, and usually the weight it's actually landed on the conductor. Okay, so you create you have something called the casing hanger, the ball of the conductor, where you hang the new one, the surface casing. Okay, then you have one more which is going to be hanged on the previous, and so forth, and you continue like that for all, even for the tubing. Okay, sometimes of course you hang it here, so you have some location where you can hang it here, for example, if you have a liner, but still the weight is going to be transferred to the previous. So you see here, I'm not sure if you see the point, maybe use the arrow, but this one is laying the weight here, is supporting or leaving the weight on the previous, and this one is leaving the weight on the previous. So at the end, the whole well weight is being carried by the conductor and being transferred to the soil by the conductor. Okay, by here in this part where it's in contact with the soil, that's where you are leaving all the weight to the contour. Okay. Now for so that's for platform wells. So for platform wells and for say not moderate low water depth, for shallow, okay, water depth. Okay, I drill the same way that I do onshore. Okay, so actually the conductor, okay, in the platform it goes all the way to the platform. Okay, simply wells are drilled just like onshore. Okay, where simply you simply extend and you sometimes see on the platform, for example, okay, on the jacket, okay, that they have, I'll make it with another color. Okay, that you have some structure that they keep it aligned. Okay, so that they keep it straight, depending on the water depth, but usually there are some guides that keep it vertical. Okay, but when we go for higher water depth, for deeper waters, then what we have is actually we have for deeper waters, okay, we simply have another system in which we have, so we still have on the seabed, and now we call it the mud line. Okay, we still have that conductor. Okay, we still have the surface casing, intermediate casing, etc. But now we have, so this becomes the seabed or the mudline wellhead. Okay, and then we have a riser that is connected to that wellhead. Okay, and then you have the hanger, the tubing hanger, up on the structure. Okay, so here you have the tubing, so that will be the tubing, and here you have, remember that between all of these hangers, okay, we usually have some packer, okay, that is actually avoiding that there will be a leakage from. This is protecting, because remember the high pressure area is going to be here. That's what is carrying. If we prolong this part here, this is exposed to the full pressure of the reservoir. Okay, this part. So this high pressure, and this pipe is made, the internal pipe, the tubing, and the production casing, they're made to tolerate that pressure. But if these pipes outside, they're just for structural. They are not made to tolerate. They're much thinner than the inner pipe. Okay, and they're also much bigger. So you will need a very big thickness to make them tolerate that pressure rating. So these leakages are actually to protect that pressure. This pipe won't be exposed to that pressure. Okay, because if that happens, it will burst. Okay, so you have the hanging part, but you also have the packer, which is, or the seals, which are supposed to protect, not packer but seals that are supposed to protect the inner pressure, the inner layers, the outer layers from the pressure on the inner layers. Okay, so you have in offshore, okay, when you have deeper waters, okay, that means, for example, here we're saying that's for TLPs, that's for spars, okay. They have this system in which you have a wellhead in the mud line, and then you have like a secondary wellhead and Christmas tree, on the structure. Okay, so that means that you have to have they are holding the weight. Actually, this weight is being carried by the structure. Okay, the weight of all of these parts. Okay, the weight carried by the structure. Okay, and that's a bit how it looks like. So essentially, let me try to make a sketch. For example, you have a spar. I'm out of space. Let me just keep. Okay, let me just add one more page. I actually had one more page, but I don't know what happened. Okay, for example, on the spar, okay, let's make the hole, and here we have our, we should make it a bit thicker. We're going to take a break zone, don't despair. Okay, you have, that's a spar, that's the mean sea level. Okay, then you have the top side. Okay, and then you have this well might be here, then you have the riser. Okay, and that's actually more or less is tension. Okay, so then you have here, you have a deck where you have the connection. Okay, and this guy is moving up and down. Okay, the spar is moving, it's a floating structure, so it might be like it has, I think typical movements are 3 meters of the spar up and down. Okay, we still is a quite a big okay, change. But then you have like a flexible connection, like a hose, like a flexible connection. Okay, and that's the riser. Okay, let me see. Okay, this we call a riser. Okay, so that's the riser, and then you put some. Sometimes you do it with two systems. These are some cans, okay, that have air cans, so flotation cans. So while this is the riser, well riser is still in place, okay, but the spar is moving up and down. This, let's call it, this is a spar. Okay, then you can still with the flexible hose you can still just allow the movement. Okay, but you have to hold, these flotation cans are holding the weight of all of these. Okay, are holding the weight of the riser, and are holding the weight of the tubing, are holding the weight of the Christmas tree that is up here. Okay. So this, now before we go to a break, this is how it looks like. Okay, and now the full sketch. So you have the well bore, you have the first wellhead, and then you have the riser, the well riser that is only connected to the annulus and the tubing. Then you have these air cans that are holding up, and then finally you have here the Christmas tree. Okay, so you see here another buoyancy can guides. Of course, you have in the spar you might have other wells that have the same configuration, that each one has their own can. I'm going to make the drawing even messier. So you need to have some sort of guides, okay, to be able to put all of these wells inside. And here you have this flexible flow line, and then you have finally the manifold where all of these wells are connected. Okay, and you have here the reference if you want to read. You see these buoyancy cans, and you have the guides, which are these structures here. And this is part of what I mentioned before, that really real estate in the offshore structure is critical. So if I'm not sure if I need 40, 20 wells, I don't want to drill more, because that will make the spar, the structure, the weight, everything will make it more costly. Okay. Here you have another system in which instead of using floating cans, I simply use this motion compensation system. It's exactly the same, but now instead of having the air cans, I have this load ring and I have this active compensation. Okay, just like in drilling, offshore drilling, that they keep it up. Then I have a roller that allows this, in this case that's a semi-sub, to go up and down, and you have the Christmas tree. And here you still need the same arrangement. You still need to have a flexible hose, and here you enter into the production manifold. Okay, because remember, this guy is moving up and down, okay, but this guy is fixed. Okay, we say fixed, or is relatively fixed. Okay, while in this case is a semi-sub, is moving. Okay. And only floating structures, spar, TLPs, and semi-subs are not that much used, have small movements, range suitable for dry Christmas trees. Okay, FPSOs definitively not. Okay, I hope I have still people here. 5. Okay, I'm not sure what happened with the rest. But let's take a break until 11:25, and we take the last part of the lecture. Do you have any questions before we break? No? Okay. See you in 11:25. Oh, Maria is writing something? No question. Okay. I'm glad to hear at least there is someone there. Okay, see you 11:25.